This video is an overview of Section 7.7 in the textbook covering confidence and prediction intervals. In this section, we learn how to create and interpret a confidence interval for the population mean response for a specific x value, x nu. We'll also learn how to create and interpret a prediction interval for the expected response for a new x value, x nu. We'll also view both the confidence interval and prediction interval on a scatter plot. To find the confidence interval for the true mean response for a specific value of x, x nu, we will use the estimate for mu nu hat plus or minus the t star multiplier with n minus 2 degrees of freedom times the standard error for the estimate of mu nu hat. The standard error equation may look a bit complicated, but we will use R to calculate it. This formula combines the variability in the slope estimate, the standard error of B1, scaled based on the distance between x nu and the mean of x, x bar, and the variability around the regression line. Since our confidence interval will be centered on the estimate for mu nu hat, calculated with a specific value of x, to interpret the confidence interval, we would say, for an x value of x nu, we are x% confident that the true mean of y is between our lower limit and upper limit of the confidence interval. We will work through an example similar to the one in the book. Here we will predict the average blood alcohol content for a student who drank 4 beers and find a confidence interval based on that prediction. Let's use the R output to find the estimated regression line. From the linear model output, we get a y-intercept of negative 0.013 and a slope of 0.018. To predict the average blood alcohol content for 4 beers, we will plug the value of 4 into the regression line for the explanatory variable, number of beers. The predicted average blood alcohol content is 0.05915 for a student who drank 4 beers. We can also use this code to find that predicted value. We see that same predicted value here. To calculate the 95% confidence interval, we need the estimate of the mean blood alcohol content, which we already found using the regression line, the t star multiplier with n minus 2 degrees of freedom. In this data set, there were 16 students, so the degrees of freedom is 14, and the standard error of the estimate of the mean blood alcohol content. Using this code, we can get all the values needed to find the confidence interval. Here is the estimated mean blood alcohol content, mu nu hat. Here is the standard error of mu nu hat. Our degrees of freedom here we can see is 14. And we'll get back to what this other value, the residual dot scale, is in a little bit. This code will give us the t star multiplier with 14 degrees of freedom, 2.1448. Putting this all together, we have our estimate plus or minus the t star multiplier with 14 degrees of freedom times the standard error. And this gives us our 95% confidence interval, 0.04735 to 0.0709. We can also use this code here to get the same confidence interval. Notice we use interval equals confidence to get the confidence interval for the predicted true average blood alcohol content for a student who drinks 4 beers. This gives us our estimate. And here is our lower confidence value and our upper confidence value. Notice that this confidence interval is really close to the same that we found above. To interpret this interval, we would say we are 95% confident that the true mean blood alcohol content for 4 beers consumed is between 0.0474 and 0.0709 grams per deciliter. Next, we will find a prediction interval for the response variable for a new value of x. The center of this interval is the estimate for the response variable, y nu hat. The equation for the standard error of this estimate includes the variability of a new observation in sigma squared hat. In other words, the standard error for y nu hat is the square root of the standard error mu nu hat plus sigma squared hat. Let's look back at the R output to calculate the 95% prediction interval for the blood alcohol content for a new student who drank 4 beers. We will again center the interval on the predicted value for the average blood alcohol content for a student who drank 4 beers, 0.05915. The t-star multiplier is the same, but we need to find the new standard error. From the output above, we find the standard error of mu nu hat and the value for sigma hat. To find the standard error, we would take the square root of the squared standard error of mu nu hat plus sigma hat squared. And that calculation is right here. And this gives us a standard error of y nu hat of 0.0227. Now we can calculate the prediction interval using our estimate plus or minus the t-star multiplier, 14 degrees of freedom, times the standard error. So our 95% prediction interval is 0.0137 to 0.1046. We can also use this code. Note that we use interval equals prediction to find our prediction interval. This should say prediction. Note that this interval matches what we found above. To interpret the 95% prediction interval, we are 95% sure that the observed blood alcohol content for a new student drinking 4 beers will be between 0.0138 and 0.1045 grams per deciliter. We can also create a scatter plot that shows the confidence interval and the prediction interval for all values of x. The blue line is the estimated line of regression. The red dashed lines show the 95% confidence interval, and the gray dashed lines show the 95% prediction interval. Notice that the confidence interval widens as we move further away from the mean of the x values to the edges of the observed x values. We can also see that the prediction interval is wider than the confidence interval, since we must account for both the uncertainty in the mean and the randomness in sampling a new observation.